Okay, we are at lecture exercise 5D. Okay, so it's the same thing. We have this aldehyde. So again, we probably number this as carbon number one, and then we have this interesting looking molecule here. So we just put this two, and if you try to translate it over to the product, so this is two, and this is one. And pretty obvious from here that something is going on between one and two, allowing them to connect together. Let's not go too far away from H2. If you have an aldehyde here, simply just an aldehyde, the most likely reaction is going to undergo would be nucleophilic kind of addition reaction, right? And in that particular case, I will therefore need a nucleophile. So the nucleophile must definitely come from carbon number two or this particular molecule. Okay, so before that, we look at the reagents here. So we have this particular interesting reagents. Um, this is some form of a secondary amine, likely to be a source of a weak base where it helps to perform some form of a deprotonation. And this is benzoic acid catalytic, so likely to be the um, acid source. And then you have a solvent here, benzene and the reflux. Normally, as you might have learned for H2, the the stuff written below the arrows, usually the condition, the solvent, etc. So those above the arrows, they will usually be like the small reagents or the catalyst that is used. It's not always the case, but you can use that as a guide to help to draw mechanism. Okay, so without actually going into the real mechanism, it actually showing you how to do the protonation step, which you have seen in the first three examples. I will simply just draw for you the final product. So assuming that protonation takes place, you're going to get a protonated aldehyde, which will look something like this. Okay, so this will be the protonated aldehydes. Okay, and of course, I need to put in the arrows here to show that is indeed being protonated. Okay, yep. Then how do I actually generate the nucleophile? Well, this part this particular species, we need to expand it a little bit because you might be wondering why are there two ester groups there. Well, if you are kind of sharp enough, you know that esters are uh, actually pretty good electron withdrawing groups, which will help to stabilize the negative charge. So just going to draw one as the okay, actually I can draw both. Okay, and then just going to put the O here, the O here, and then the OET. Okay, and then OET as well, and then I'm just going to resize it to make it look okay. So you notice that this particular CH2 group, okay, I'm going to put hydrogen in here, is actually flanked by two highly withdrawing oxygen here. Okay, and with the catalytic amount of benzoic acid, you might expect some form of protonation on one of the carbon oxygen, which is fine. Okay, so I think you just have to put that in here. Yep, and then if you're going to show the mechanism, it will be good habit, okay, to actually show the deprotonation step because this is probably one of the most crucial steps that will I mean we will get to see whether you do understand your basics or not. Okay, so this lone pair actually helps to deprotonate, okay, and then form the pi bond, and then flow towards the electron sink, which is the protonated OH. Okay, so when this happens, this is what you're going to get. Okay, I'm just going to do it very quickly. Okay, so you're going to get a pi bond that's formed over here. Okay, something like that. And remember, whenever electron density actually flow to the electron sink, the lone pair now it's formed on the oxygen, right? So now I'm going to have a lone pair here, and this whole system become an electron uh, source. Okay, starting from the O. Okay, right. So okay, so I'm just going to shift this a little bit to my right. okay, just a little bit to my right, and then I'm going to shrink this main group that I'm going to deal with here. Okay, so now you're going to have these two molecules coming together. Okay, I'm going to number the carbon again. So this is 1, and this is 2. Now, carbon number 2 is going to be the electron-rich site. Carbon number 1 is going to be the electron-deficient site. Yeah, so this is going to resemble what you have learned in H2, nucleophilic addition. Okay, except that in H2, in most cases, the nucleophile is a simple cyanide or maybe just a simple green out reagent. But here you have to generate the nucleophile, and again you have to generate the electrophile. Okay, on your own. Okay, so I'm just going to combine the two together, and then you're going to see that the answer is kind of actually relatively straightforward, although it's not. Um, it may not appear as straightforward as what you expect initially. Okay, so I'm just going to okay, I'm just going to extend the arrows a little bit. Okay, yeah, now it makes a little bit more sense. Okay, so again, remember, when you push arrow, you push from the electron source to the electron sink. So the electron source is the lone pair of OH. So you flow from the pi bond, and then this reactive pi bond, the nucleophilic carbon 2, the pi bond will then attack the electron deficient carbon number 1, and then electron that's made from the CO pi bond will now flow towards the OH. So again, let me reiterate, the protonation of the OH is really to make the carbon-on-carbon more electron deficient. So when this thing happens, okay, I'm definitely not going to redraw the whole thing out. I'm just going to cut and paste. So just going to copy this over here, push it down. Okay, okay, I'm just going to erase the numbering. Okay, a little bit. Okay, okay, just going to write out the OH here. Okay, OH. Okay, and then just going to redraw this out so that okay, right. Now it makes perfect sense. OET. Okay, and it's smaller, and then of course it will be protonated as per what we drew earlier on. It has to be protonated. Okay, so remember your charge. Okay, make sure that they are conserved. So very often when we actually get the students to do the work, yes, so okay, so this should CO2ET. I think I made some mistakes here, but it's okay. I think it's easily reconcilable. Okay, yep. And then when this happens, you're going to get an OH here, and then so what's going to happen next? Will there be intramolecular proton transfer? Okay, yeah. So most of the time when we reach here, it's very close to the answer. Okay, it's very close to the answer. So most importantly, you when you finish off your mechanism, you really need to ensure that things are actually in place, because all your effort will be gone to a waste if you draw until here and then you anyhow complete the end. Remember that you're going to form a pi bond here, and the reason why you're going to form a pi bond here, the driving force is really because of the extended conjugation between the phenol ring, the CO, and this particular pi system. Okay, so we can begin by doing an intramolecular proton transfer, which I'm not going to really draw out the mechanism. Okay, just for simplicity, I'm just going to shift this over here. Okay, and then what's going to happen is that if you really just want a quick one, you can simply lose the H as a H plus, and then you can kick out the OH as a leaving group. Sorry, the H2O as a leaving group, and then in this case you actually form the pi bond. Okay, some of you might heard of this mechanism known as E1CB, first order elimination conjugate base, but we're not going to talk about that in our case here. So for the purpose of this particular exercise, if you're able to draw something like that, I would say it's already very good. Okay, yep, and E1CB is usually driven by the presence of a strong base. In this case, this particular mechanism is actually acid catalyzed. Of course, you are not sure what is the use of this particular amine besides uh, acting as a source of base. Okay, so without further details, there isn't really a need to consider every single angle. What you are supposed to draw is a plausible mechanism. It's not a mechanism that is an absolutely correct one. Okay, so remember this is proposed mechanism, as close to reality as possible within your means, but definitely the truth is you want to study the real mechanism, you still need to go for the kinetic studies. Okay, yep.